Let's say we want to calculate an upward orientation of f of xy equals xy. So I'm going to let x equal u, and I'm going to let y equal v. So z, which equals xy, is going to end up equaling uv. So my r of uv is going to end up equaling u v uv. I'll start out with tu. Tu is going to end up equaling 1, 0, v. tv is going to end up equaling 0, 1, u. We'll take their cross product. So we get negative vi minus uj plus 1k. We'll take its magnitude. Magnitude of that, it's going to be negative v squared plus negative u squared plus 1 squared. So this ends up being equal to the square root of v squared plus u squared plus 1 squared. Plus 1, excuse me. So our normal, or our unit normal, is going to end up equaling negative v, negative u, 1, divided by the square root of v squared plus u squared plus 1. One thing to notice here is that the 1 is positive. So I've got a positive 1 for z. So this orientation is facing upward. Right? Basically, we're moving in the upward direction. Doesn't really matter what u and v are in this case, because z is constant. In addition to that, by the way, I guess I should add to that, this is always positive since v is squared and u is squared. Okay? So that gives me my upward orientation for this particular vector. Let's say we want to calculate an upward orientation of f of xy equals xy. So I'm going to let x equal u, and I'm going to let y equal v. So z, which equals xy, is going to end up equaling uv. So my r of uv is going to end up equaling u v uv. I'll start out with tu. Tu is going to end up equaling 1, 0, v. tv is going to end up equaling 0, 1, u. We'll take their cross product. So we get negative vi minus uj plus 1k. We'll take its magnitude. Magnitude of that, it's going to be negative v squared plus negative u squared plus 1 squared. So this ends up being equal to the square root of v squared plus u squared plus 1 squared. Plus 1, excuse me. So our normal, or our unit normal, is going to end up equaling negative v, negative u, 1, divided by the square root of v squared plus u squared plus 1. One thing to notice here is that the 1 is positive. So I've got a positive 1 for z. So this orientation is facing upward. Right? Basically, we're moving in the upward direction. Doesn't really matter what u and v are in this case, because z is constant. In addition to that, by the way, I guess I should add to that, this is always positive since v is squared and u is squared. Okay? So that gives me my upward orientation for this particular vector. Now that we've thought about calculating orientation of an integral, which is going to end up becoming kind of really important for us, we now want to think about flux. And because flux is one of the major ways of thinking about working with surface integrals. Okay? So if you remember, the flux for a line integral was the amount of, or the amount of flow that was going through that line. So it was, you know, is a one-dimensional surface, okay? So it's basically just the single line, and we wanted to kind of imagine if you're going like normal to that surface, how much of whatever it was like a liquid or, you know, electricity was flowing across that line. Now what we're going to do is we're going to imagine that we got basically the same thing. But instead, we've got a surface. So we're going to imagine the surface, and the phrase they use is is that it's permeable. Perfectly permeable. You can flow out. It's not going to block anything. It's basically like a measurement device, right? And so essentially what's going to happen is as this liquid flows across it, we're going to measure the amount of flow that is going through this surface. And so you've got, like I said, we've got this surface. We're going to calculate that amount of flow for the vector field. And if you think about it, that flow is going to be dependent upon whether or not we're going to have like an outward orientation or an inward orientation or an upward orientation or a downward orientation. Okay? And if you also remember when we were calculating flux with the line integrals, we used this f dot n ds, which the little s, which was our basic equation. It's going to be the same thing. It's going to be that vector field f dotted with the normal, and then we're going to take it and multiply it by big ds, okay? And that's going to end up giving us the value for our flux over this particular vector field. So now we're thinking about calculating flux. Let's imagine we've got a surface again, okay? So here's our surface, and we're thinking about, like, here's our vector field, and our vector field's moving through this surface, okay? And we're trying to figure out what's the flow, okay? What's the flow of that vector field through that surface? If you're imagining like a liquid, it's like, what's that rate of flow as it moves through the surface? And basically what that is, how we calculate that, is we're going to calculate that as f, the vector field dotted with the normal vector n, okay? And we'll select like a tiny little piece here, and we're going to, basically calculate f dot n. That's going to be the flow over that tiny little piece. And so we'll need to then multiply that by the area of, we'll call this Sij, the area of that surface integral. So we're calculating f dot n in that area, okay, in that little area, and then we're multiplying it by the surface area of the region, okay? So that's kind of the idea, right? And so basically what ends up happening, right, is that you do this for all of these different areas that are on the surface. So you're finding f dot n. And by the way, we should think about it f dot n at a point pij. It's some point pij and sij. We do that everywhere, okay? And then what do we do with it? We add it all up. We accumulate it. And once we accumulate it, what we end up getting is, so the accumulation of all of this is our flux. Okay, so that's the accumulation of all of this that ends up giving us our flux. So if we go in and we add those all together, we're going to end up with an integral. We're going to end up with an integral over the region D, and it's going to be f dot n, right, ds. There you go, and that equals the flux. Notice how similar that is to the flux for the line integral. Super duper similar, okay? The flux for the line integral was just a little s there. Okay, and it was over the curve C. All right, so this function right here, the double integral over the surface of f dot n ds, which is our flux, can be a little gnarly to integrate. It actually can be kind of like wearying, in fact. So what we're going to do is we're going to actually simplify it. We're going to get s of f dot n ds. And we know that n is, so we got now, this is s of f dot, and this will be tu cross tv over the magnitude of tu cross tv, okay? And then this is ds. And what we'll do is we'll actually change this to an area integral, all right? So we'll have this equal to then the double integral over the area d of f dot tu cross tv over the magnitude of tu cross tv, and then what happens here then is that this then becomes multiplied by tu cross tv magnitude dA. All right, remember that, like our ds is basically equal to this, okay? And we just change it conceptually to, like, I've got a region D and I'm going to calculate this over the region D. These cancel, and so now over this region D, whatever that is, we got f dot tu cross tv okay, dA. If we go in and we replace with our parameterization, this is going to equal the double integral of d of f dotted with tu cross tv, okay, f of r of uv, right? So we just put in our parameterization and then dot it with tu cross tv, dA. And that actually gives us the value for our integral, okay? A lot easier to work with then. And this thing here, we write this generally as, so let's look at an example. Let's actually just set this up. You can utilize a computer in order to integrate it. What we've got here is we've got our surface integral f dot nds. We're looking for its flux. And we have f is negative y x 0. And s is our surface that's parametrized as r u v, u, v squared minus u plus v. And we're going to go 0 less than or equal to u less than or equal to 3. V greater than or equal to 0 less than or equal to 4. So our vector field f, okay, so f of r of u v is going to end up equaling, we've got negative v squared minus u, and then we've got next up is x, so u, and then finally z is just 0, okay? And there we go, there's our force field. Tu, we're going to utilize r of uv, okay, so tu is going to end up being 1, negative 1, 1. Tv is then going to equal 0, 2v, 1. We'll take the cross product of the two of those. So the cross product, I've got 1, negative 1, 1, 0, 2v, 1. So that gives me, that's going to end up being negative 1 minus 2v I minus 1j plus 2vk. Okay, and there's my cross product. So now I've just got to take the, I've got a dot f with tu cross tv. So this is tu cross tv. So I'm going to take negative, or we'll take u minus v squared, u, 0, dotted with negative 1 minus 2v, comma negative 1, 2v. And that'll end up giving me 2v squared, or 2v cubed, excuse me, plus v squared minus 2uv minus 2u. And now all we need to do is we just need to integrate over the area of this rectangular region. So we're going to go from 0 to 3, 0 to 4, and we'll integrate the function 2v cubed plus v squared minus 2uv minus 2u du dv. Let's suppose that what we want to do now is we want to calculate the mass flow rate, okay? Basically, we're calculating flux, right? The mass flow rate, that's essentially our flux, it's f dot nds, or f dot s, like if we're thinking about from the perspective of our surface integral. So we've got this surface, v of xyz is 2x, 2yz, and it represents a velocity field with units of meters per second of a fluid with a constant density 80 kilograms per meter cubed. And we're going to let s be the hemisphere x squared plus y squared plus z squared equals 9, with z greater than or equal to 0, such that s is oriented outward, right? We want to find the mass flow rate of the fluid across s. Now, we're looking at a sphere, a hemisphere x squared plus y squared plus z squared equals 9. So my parameterization, I'm going to want to make sure that I use spherical in order to do this, okay? Remember that spherical is going to have x equals, and it's going to be rho sine, rho cosine theta sine phi. Y is going to end up being rho sine theta sine phi. And z ends up equaling rho cosine phi. In this case, rho is 9. Okay, so our parameterization, or the parameterization of our surface, we can use r of, and we'll call this theta phi, as being equal to, or rather, let's do phi theta. We'll find Tu first, or rather T phi. Okay, T phi is going to then equal 3 cosine theta cosine phi, 3 sine theta sine phi, and then negative 3 sine phi. This would be a cosine phi. T theta is then going to equal negative 3 sine theta sine phi, 3 cosine theta sine phi, and then 0. When we take the cross product, T phi cross T theta, what we end up getting is 9 cosine theta sine squared phi, 9 sine theta sine squared phi, and 9 sine phi cosine phi. There are a couple things that we can actually notice or note. Okay, one is that if we've got sine phi cosine phi, or well, that each one of the values here, what we want to notice is that each one of these components of the cross product ends up being positive. And since each one of those is positive, this indicates that we have our outward orientation. Okay, so that's actually going to give us our outward orientation. So we can utilize T phi cross T theta. Now we're going to take F. Well, F of, in this case, R of UV. We have to plug in our parameterization. This is going to end up equaling 2 times 3 cosine theta sine phi, and then 2 times 3 sine theta sine phi, and 3 cosine phi. So this vector field, right, we plug in our parameterization, okay, into our vector field, all right, and what we end up with is our force, our vector field under the parameterization R of UV. Now we're going to take F and we're going to dot it with T phi cross T theta. Okay, so we'll go in, we'll dot it T phi with T theta, and this ends up giving us, after some calculation, I'll have you go in and do the calculation, pause this for a second, 54 sine cubed phi plus 27 cosine squared phi sine phi, and that's the function that we'll be integrating. So we'll go in, we'll take the double integral, and again, because we're looking at just the hemisphere, right, that half sphere, right, x squared plus y squared plus z squared, that's going to have our theta from 0 to 2 pi, and our phi from 0 to pi over 2, okay? So we'll go from 0 to pi over 2, and 0 to 2 pi for our hemisphere, and this will be then 54 sine cubed phi plus 27 cosine squared phi sine phi, and that'll be d phi d theta. Take a moment, pause, so you can go and calculate this. This will end up giving me 7,200 pi. So when I go up and plug in my the values that I have here, 80 kilograms per meter cubed, that's my density, okay? And then my time is the seconds. This is going to be 7,200 pi kilograms per second per meter squared. And that is my answer, okay? A bit involved, we didn't go through all the calculation, but just kind of see that what we're doing here is the same basic process, okay? We went in, we parameterized our surface, right? Then we took the parameterization, I found T of the tangent vector for each one of the components, took that cross product, then I figured out what my force field is, my vector field was in terms of my parameterization. I dotted those two, and then I took the double integral over the region, okay, with respect to, in this case, d phi d theta, because those were our variables of integration, okay? And there we go. That's essentially it. That's what you're going to be doing. So calculating the surface integral over a vector field is the same as calculating the flux over that vector field. All right, so those two things are the same. What we looked at is we looked at a much simpler way of calculating the value for flux. All right, utilizing that basically F dot TU cross TV. All right, using that equation in order to help us calculate our flux. So basically, what you want to do here is you kind of want to like look at it. You say, all right, I need to plug in my parameterization into my vector field. I need to calculate TUs cross TV, find their dot product. Okay. And then integrate, and that's how you calculate your flux over a surface. Over a surface.